We present our work on 3D shape modeling using multi-view depth maps. In past couple of years, there have been rapid advances in representing and synthesizing images using deep generative models. These advances can be attributed to both improvement in neural network architectures as well as large-scale image datasets. The objective of our work is to repurpose the models used in image domain for the domain of 3D objects. In contrast to images, there is no global standard for representing 3D shapes. There are a number of representations available, each with its own pros and cons. We argue that multi-view images are better suited over its counterparts for the purpose of modeling 3D shapes using a neural network. Our framework consists of two modules that are trained separately. First is an encoder-decoder architecture that finds a view-independent representation of a 3D object. The second module learns a generative model over the representations learned in the first part. Let's go over the first module in a bit more detail. Input to this module is an image or a depth map of the object taken from an unknown viewpoint. The identity encoder, which is a CNN, maps the image to a 1D latent vector. We encode multiple viewpoints of the same object during training. We then use a simple average pooling to get the latent representation of the object. For decoding, we convert this latent representation to a style vector using a multi-layer perceptron. This style vector is combined with viewpoint embedding to generate a depth map. We compute depth map from multiple viewpoints, and then we finally compute an L1 reconstruction loss. Our encoder-decoder framework can easily perform reconstruction of 3D objects from a single viewpoint. Here are some of the results. The grayscale columns are the depth map inputs to the network, while the colored columns are the reconstructions from the depth maps generated by our model using 20 different viewpoints. Our model learns a smooth latent space. We can demonstrate this by interpolating between various objects. Here is a TSNE scatter plot of 59 ShapeNet class embeddings learned by the model. We see that visually similar embeddings categories cluster together even if they are not semantically similar. Our second module is an implicit maximum likelihood optimizer which maps random point sample from a Gaussian to 3D shape priors. Implicit MLE offers several advantages over models like GAN, such as stable training and no mode collapse. We start with a batch of real data points represented by red squares. A generator, which is a fully connected neural network, maps random noise samples to same dimensional space as real data points. For each real data point, we select the closest generated point, and then we compute our loss function, which tries to minimize the distance between real and nearest generated points. Here are some of the samples as generated by our model. Visit our websites to check out our work and for more results.